Okay, completing the square. What's going on here? So we left our last video, the last video that we looked at, we left with a question. If we had y equals 4x squared plus 20x plus 7, find vertex, central axis, range, x and y intercepts, and graph it. Right? And that's not that easy, right? Because this is not in a form where you can just read off, well, it's been moved left and up and then rescaled by this, that, or the other thing. So we have to be able to figure out how to put it in that form. So what's the basic idea of completing the square? Well, the idea is that if you have, say, x squared plus 2x, right, the first two terms of a quadratic, right, not the whole 4x squared plus 20x plus 7, but just say x squared plus 2x, there's a particular magic number, in this case it would be plus 1, that allows you to write it as x plus 1 quantity squared. So x squared plus 2x plus 1 factors to x plus 1 quantity squared. What about x squared plus 4x? What's the number that you have to add here to get a perfect square, to be able to say this is x plus something squared? Well, in this case it would be 4. And that's x plus 2 quantity squared. Because if you multiplied out x plus 2 by itself, what do you get? You get x squared plus 2x plus another 2x, that's a 4x, and then the last two terms would give you a 4. Okay. What about x squared plus 6x? What's the third term that you have to have here in order to make it a perfect square? X plus what? Well, it'll have to be 3 here, or 9 there. So x squared plus 6x plus 9, that's x plus 3 quantity squared. If you multiply out x plus 3 quantity squared, you get a 3x and another 3x, that's my 6x, and a 9 is the 3 times 3. The 4 is the 2 times 2. The 1 is the 1 times 1. And whenever we multiply out a perfect square, we always double this term, right? X plus 1 quantity squared, you get 2x. X plus 2 quantity squared, you get 2 times x plus another 2 times x, so that's a 4x. You get a 3x plus another 3x, so that's 6x. So if we had, say, x squared plus 10x, what would that have to be? Well, these numbers are always twice these numbers, right? Twice 1, twice 2, twice 3. So if we had a 10x, it would have to be a 5. This number, the constant, that's this number squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 5 squared is 25. So x squared plus 10x plus 25, that's x plus 5 squared. So if I have the first two parts of any kind of quadratic, what I can do is say, well, what does this number have to be that I have to add to it to get a 3-term thing that collapses into x plus something quantity squared? And we like x plus something quantity squared because this is a parabola that's been moved 5 units to the left, right? X plus 5 quantity squared, that's 5 units to the left. Okay, so suppose we look at an example. X squared, y equals x squared plus 6x plus 14. And we want to know all the usual stuff about a parabola for this thing. But we don't know, we don't have it in the right form. Well, we know 6, right? So we have x squared plus 6x. What should the number here be to make it a perfect square? Well, we've seen that. X squared plus 6x plus 9. Right? That's going to be a perfect square. So we take our y equals x squared plus 6x, and we say, well, we need a plus 9 there to make it a perfect square. But I don't want to imbalance the equation, right? It's y equals something. I can't just add a 9, right? So I'll subtract a 9 at the same time. Because 9 minus 9 is 0, what's happening here is that I'm not adding anything or subtracting anything, as long as I have a plus 9 minus a 9 right after it. But the magic of that is that I get to regroup everything. There's that bit. And then minus 9 plus 14. This bit I know is x plus 3 quantity squared. Minus 9 plus 14 is plus 5. So now I've rewritten this as this. I can't tell by looking at this just where it is. Has it been moved left, right, up, or down? I can look at this and say, well, it's been moved left 3, up 5, and not been rescaled at all. So if I graph this function, I need a little more space there because if it's been moved up 5, so left 3, up 5, so there's my vertex. Not been rescaled, so 1 unit over, 1 unit up, 1 unit over, 1 unit up, and it looks like this. So vertex minus 3, 5, central axis x equals minus 3, range, it's opening up, so the vertex is at the bottom of the range, so it's y greater than or equal to 5. Y-intercept, well, we'll have to plug in x equals 0 into a formula. We actually have two formulas to plug it into. We could plug it in here. If we plug in x equals 0, we get 0 plus 14. That says that the y-intercept should be 14. If we plugged in 0 here, we get 0 plus 3 quantity squared. That's 9 plus 5. Well, that's also 14, which is really good, right? Our two formulas are supposed to represent the same function, so if you plug in x equals 0 into either one, you should get out the same number. So the y-intercept is y equals 14, which is off the top of the graph somewhere. And the x-intercepts, well, there are no x-intercepts because it opens up and its vertex is above the x-axis. So there we go. We have now figured out what's going on. And so the key, of course, is this 6. And I need to be able to take this 6 and go from the 6 to saying that there's a 3 there. And what's the relationship between these numbers and these numbers inside the squaring? Take this thing, cut it in half. 4, half of 4 is 2, half of 6 is 3, half of 10 is 5. Once you know these numbers, then you square these numbers to get what you have to add. 1 squared is 1, 2 squared is 4, 3 squared is 9, 5 squared is 25. So let's do another example. Suppose we have y equals x squared minus 4x plus 3. So take half of this is minus 2 and then square it. And that gives us these two numbers, minus 2 and 4. So we can take this number, the squared number, and say, okay, x squared minus 4x, add the squared number and subtract it right away to get that. And again, 4 minus 4 is 0, so all we've done is added 0. We haven't changed anything. But the first three terms now can be factored into a perfect square. And what is the perfect square going to be? It'll be this number. So x minus 2 quantity squared minus 4 plus 3 is minus 1. So again, we can graph this. We can actually, now that we've done a couple of cases of this, oops, don't need the central axis, we can say, well, we know where the vertex is because the way it's written, it tells us that it's been moved right 2 units and down 1. So our vertex is going to be at 2 minus 1. And then it's not been rescaled. Oops, sorry. The central axis is x equals 2. The range, since it's not been flipped, right, we know that the range has to be bigger than the y value at the vertex, so y has to be greater than or equal to minus 1. Y-intercept, well, we have two formulas to find the y-intercept from. this one or this one. So we can find the y-intercepts by setting x equal to 0 in either one of those. So it'll be set x equal to 0 here, that'll give you 3. Set x equal to 0 here, that gives you minus 2 squared, which is 4 minus 1. Y equals 3. And of course, to find the y-intercept, you set x equals 0. Now we know that 0 is greater than minus 1, so 0 is in the range. That means there are x-intercepts. So what are the x-intercepts? Well, again, we actually have two formulas. Set y equal to 0, solve for x. So let me just put in a big bracket for this. We can do this one of two ways. We can take this formula, 0 equals x squared minus 4x plus 3. And solve that for x. There's a number of ways to do it. The easiest way to just be to factor it, which will give you x minus 3 and x minus 1. Right? Plus 3 minus 4. So x equals 3 or x equals 1. Those are my two x-intercepts. Or we could solve it by using this equation. 0 equals x minus 2 squared minus 1. Move the minus 1 over to the other side. 1 equals x minus 2 quantity squared. Take the square root of both sides. Square root of 1 is plus or minus 1. It's a square root, so you got to pick up that plus or minus 1. X minus 2. And so 2 plus or minus 1 equals x. 2 plus 1 is 3. 2 minus 1 is 1. So those are my x-intercepts. Great. And so with that information in mind, we can sketch what our graph looks like. The vertex was at minus 1. The intercepts, x-intercepts were here and here, and the y-intercept is at y equals 3. So our parabola looks like that. Okay. So, not too bad. Often in these problems you'll start with a formula, translate it into another formula. This is much easier to graph. It's also much easier to read off what the vertex, the central axis, and the range is. You can get the x-intercepts and the y-intercepts from this formula or from this formula, depending on what your taste is in those types of matters. Okay, so what about the problem that we left at the end of the last video? What about y equals 4x squared plus 20x plus 7? This is a problem, the 4 times the x squared. Why is that a problem? Well, everything we've done so far has been based around the idea that this formula, oops, that's not an equals, that should be a plus, is true, right? If I take x plus a quantity squared and multiply it out, what do you get? X squared plus 2ax plus a squared. There's our 2a, that's why we had to divide by 2, and then there's our squared term. What this assumes is that the coefficient in front of the x squared is 1. So how do we handle 4x squared plus 20x plus 7? Well, we do what mathematicians always do when faced with a difficult problem. Turn it into a problem we already know how to deal with. I'm going to just factor out that 4. Right. So I get 4 times the quantity x squared plus 5x plus 7/4. Factor of 4 out of here, that leaves me with an x squared. Factor of 4 out of 20, that leaves me with a 5. Factor of 4 out of a 7, well, that leaves me with a 7/4, because 4 times 7 over 4, that'll just leave me with 7. Great. So now, complete the square inside the brackets. Right, so 4 big bracket, we'll make a bit longer bracket, right? And we look at this number, the 5, and we take half of that, we get the number 5 halves, and then we square that 5 halves. 5 halves squared is 25 over 4. This, the squared number, that's what I have to add and subtract. And we're just doing all this inside of the square brackets. So plus 25 over 4 minus 25 over 4, add and subtract it, plus 7 over 4. And as always happens when you do that, the first three terms are a perfect square. So this is y equals 4 times, and we'll leave our big square brackets there because we're just playing inside the brackets. X squared plus 5x plus 25 fourths, that's x plus 5 halves, quantity squared. Minus 25 over 4 plus 7 over 4, where they have the same denominator, so I just have to add the numerators. Minus 25 plus 7 is minus 18. And I guess I can move this square bracket in closer. There we go. Great. And now just distribute the 4. There we go. It's in the good shape that we want it to be. So when I have a 4 coefficient times my x squared, regardless of what it is, and it could just be a minus sign, right? There could just be, you know, minus something there. Factor it out so that you have a big bracket here where your x squared has a leading coefficient of 1. And then you can do the regular completing the square thing inside the bracket, and then when you're done, just multiply the 4 back in, and that gives you what you're looking for. So, reading this off, what's the vertex? Left 5 halves, so minus 5 halves, down 18 over 4, minus 18 over 4. That means that my central axis goes through the vertex. The range, well, it's a 4 plus 4, so it's opening up. So it's numbers above the, not minus 18 over 4, minus 18. When you multiply through by the 4, you got to remember to cancel that. So the range is y greater than or equal to minus 18 because it's a parabola that opens up, and so the range is y values bigger than the vertex. Y-intercept, well, pick one of the formulas and set x equal to 0. For my money, this is the easier one to calculate when trying to find the y-intercept. If we set x equal to 0, we get y equal to 7. So that's my y-intercept. If I have to find the x-intercepts, I generally want to deal with this formula because I don't have to remember the quadratic equation, I don't have to factor anything, it's just taking the square root. I know because the range 0 is greater than minus 18, that tells me that definitely are x-intercepts. So, what are they? To find an x-intercept, you set y equal to 0 and solve for x. So, looking at this equation, we take 0 equals 4, x plus 5 over 2, quantity squared, minus 18. Add an 18 to both sides, that gives me 18 equals 4, x plus 5 over 2, quantity squared. Divide both sides by 4, that'll give me a 9 over 2, x plus 5 over 2 squared. 18 divided by 4, you can cancel out a 2 out of everything and you get 9 over 2. And then I can take the square root. Square root of 9 over 2, square root of 9 is 3, square root of 2 is just square root of 2, and you pick up a plus and minus because you're taking the square root. X plus 5 over 2, and finally move the minus 5 halves to the other side. And as we saw before, that's a 3 over 2. Oh, as we will see, the x-intercepts have to be symmetric with respect to the central axis. And so that's why we have a minus 5 halves there. So what does the graph of this thing look like? Well, let me write down the equations again so that we don't lose track of where we are. And we're dealing with, what are we dealing with? Y equals 4x squared plus 20x plus 7. And that's also equal to, because we completed the square to get this thing, 4 times x plus 5 halves squared minus 18. Okay, so what does the graph look like? This is not going to be to scale, but I can graph it from this thing. So we'll say move left 5 halves, so we'll say that's here. Down 18, we'll say 18 is down here somewhere, so there's my vertex. Scaled by 4, so if we go 1 over, we'd have to go up 4, and so that would give me to minus 14. And then we have our 2 roots, which are minus 5 halves plus 3 halves. The y-intercept will be up about 7, and so our parabola will look like that. And if we go the same distance to either side of the central axis, we get our 2 roots. So minus 5 halves. If we go to the right, you get minus 5 halves plus 3 over root 2. If you go to the left, you get minus 5 halves minus 3 over root 2 as your 2 x-intercepts. And that's everything that we need to know about our parabola. So completing the square, it's a bit of an algorithm, a couple of steps there, but it's not too hard to do once you've done a couple of them. The biggest thing to remember is that when you have a coefficient that's not